Welcome back. I hope you enjoyed the numeric detour. We're now going to continue with our study of the IPOS programming language. This is part 2 of the learning language section. So let's go ahead and move into the next major concept. Today we're going to look at constants and variables. This is a very important concept because all programs make heavy use of constants and variables. So we need to understand how IPOS handles them and what you use them for. Now we have to cover several ideas that I consider really crucial because they have to do with the way numbers work under IPOS. And since almost everything we do involves numbers, clearly it's important we know how they're going to behave. Of course, at heart, all programs manipulate data. That's really why computers exist. And even in a control environment, that's true as well. IPOS, unlike C and other similar languages, has just one data type, and that is the number. Now, if you're a programmer, you know what data type is. If you're new to programming, maybe that's an unfamiliar term, so let me define it. Data type is a type of information. It could be numbers, it could be individual bits, it could be characters, it could be groups of characters, which are called strings, or it could be very complex structures that have many different kinds of data clustered together. The C programming language and all the derivative languages have multiple data types. IPOS, however, really has just one, and that's the 32-bit number. Now, numbers can be expressed or provided in 3 different numeric forms: decimal, binary, and hexadecimal. But they do behave slightly differently depending upon how you supply them, so this is where you really have to listen up. When you're putting a number into a variable, for example, you can supply it as decimal. Our first 2 examples here are decimal. There's 152 and negative 1873. By the way, if you put in a number without a symbol in front of it, then that will be treated as a positive number, so that 152 is actually positive 152. You can, however, if you wish, supply numbers either in binary or hexadecimal format. Now you notice there's a slight difference in how they look. They have 2 characters in front of the number itself. If it's a binary number, it's a 0 and a lowercase b, followed by the binary number. There are no spaces in any of this. And if it's a hexadecimal number, it's a 0 and a lowercase x, followed by the hexadecimal digits. That's how IPOS differentiates between decimal, binary, and hexadecimal. Be aware of that. You'll definitely see examples of binary and hexadecimal numbers as we go along in the class. Okay, as I've said a number of times, all numbers are treated as 32 bits long. That's because that's the size of data memory. So numbers are always going to occupy 32 bits. But what winds up in those 32 bits does depend on the kind of number and how you provide it. If you provide a decimal number, it will automatically be sign extended to a full 32 bits. Let me show you an example of this. If you say, for example, that the H0 variable should contain 152, which is a decimal number, that's actually positive 152, it will automatically sign extend that number to a full 32 bits, and it will do it with zeros because that's a positive number. On the other hand, if you supply a negative number like negative 1873, it will sign extend that number using 1 bits. Because remember, 1 bits indicate negative numbers. Of course, that number is actually encoded with the 2's complement system, which you learned about earlier. That's what's going to wind up in those 32 bits if you supply a decimal number. It's going to always sign extend it. Now, here's what's different. If you supply a short binary or hexadecimal number, this won't happen. It will simply pad those numbers with zeros to make a full 32 bits. So, for example, if you put in 0B1010, that's just a little binary number, it's going to pad it with zeros, which means that if you dealt with that number with a mathematical operation, it would treat it as a positive number. And if you put in a short hexadecimal number like hexadecimal 80, it would simply add enough hexadecimal digits to bring it up to 32 bits. It takes 8 hexadecimal digits to equal 32 bits, and that's it. Again, that would be a positive number. So what do you do if you want to incorporate a hexadecimal or binary number that is negative, that has a 1 in the most significant bit position? Well, the answer is don't enter it as a short number. Enter it as a full-length number. In other words, supply all 32 bits if it's a binary number and make sure that top bit is 1. And if it's hexadecimal, supply 8 digits. And of course, that last digit needs to be the number 8 or higher, 8, 9, A, B, C, D, E, or F. That will, of course, be treated as a negative number. In many cases, however, when you're supplying binary or hexadecimal, you really don't care about sign. What you're doing is supplying bits that are often used for control purposes. And in cases like that, you really don't care. Therefore, be sure you understand these differences, because if you don't, you are going to bump into some weird problems as you go along. But if you do understand them, everything should go really well. All right, constants and variables. What is a constant? Well, it's simply a fixed numeric value that has some significance in the context of the program. For example, this expression here has 3 constants in it. They're simply those hard-coded numbers. 4096, which in this particular case happens to represent how many increments per revolution the motor encoder generates. 3961 happens to represent a gear ratio. And 2001 indicates the circumference of a sprocket. So this is some kind of calculation that is working out a scale factor that incorporates the encoder, a gearbox, and the circumference of a drive sprocket. And we use constants to make this possible. You can put constants directly into your program like I've done here. So just key them in as numbers. These are decimal constants, but you could put hexadecimal or binary constants, and that would be just fine. Now, here's one of the challenges with constants. When you see a number in a program, if there isn't a comment or something explaining what it is, you really have no idea where that number came from. For example, that 3961, that's not very obvious that it's a gear ratio. And so that kind of brings us to a challenge. How do we make constants meaningful so people down the road trying to interpret your program will know what that number is? And if they have to change it, what's an appropriate value to change it to? Also, if you use a constant many times in your program, it can get really tedious typing that number in over and over and over. And of course, there's always the chance you could start making mistakes when you do that. And this is even worse. What if you have to change a program and you've got to change a constant that appears in that program 50 different times? You've got to go through and make sure you've replaced every one of those correctly. Now, maybe search and replace can help, but of course you've got to be careful with search and replace. That can bite you sometimes by changing something it shouldn't. So we have a number of challenges here, and of course I have a solution. This is a better approach. Notice those hard-coded number values have been replaced with names. These are the aliases for the constants. We can see these right here. This is nicer. These names are a lot more meaningful. They kind of suggest what the constants are. I've tried to pick some meaningful names here. So it makes the program a whole lot more readable. And also, I can just use these in any place I need those constants. I don't have to keep remembering what the number values are, so I'm not going to be making mistakes keying a number in wrong. And changes are much, much simpler. If you have to change this, you just change it in one place, the place where you set up the alias, and every place that name appears, it will automatically change. So this makes your program a lot more bulletproof, less likely to accumulate those weird little mistakes that can take forever to find. Now, please pay attention. There is a very important point you need to understand. This applies to both variables and constants, and a lot of other things in IPOS actually, because IPOS is C-based. C is completely case sensitive. That means upper and lower case are different. So it matters everywhere in the program. So you need to be totally consistent with using upper and lower case. If you make a change, even if it's just one character, then that's a different name, and that can really bite you. So it's important to be very conscientious about case, and that is true in any C-type language, including IPOS. Where do you define constants that are using this kind of alias approach? You do it right at the beginning of the program, and you do it right after those pound include commands. Remember, when we set up our skeleton program, I told you to create a comment, constants, and variables. Well, that shows anyone reading your program where those are going to be found. And you can see, in this case, they're right down here. So let's look at how we set these up. You use the pound define compiler control command. So this is another compiler control feature. It's not strictly speaking part of the language. It's something that just instructs the compiler. So right here, notice, remember, no space between the pound and the define. Traditionally, most programmers make their constants all uppercase. You don't have to, it's not a law. But programmers do it because it's sort of a clue to other programmers that when you see an all uppercase value, that probably means it's a constant. So that's just a convention. I do recommend you follow it. Also notice there is no semicolon at the end. This is another case where you don't end a line with a semicolon. And a constant can be either a simple value like a number, or it can be an expression. Let me point out an example of each. 4096 is a simple constant. It's just a plain old number. It can be any kind of number you like, decimal, binary, or hexadecimal. An expression, on the other hand, is a group of characters that means something. And you probably don't understand what this expression means. Don't worry about it. I've simply associated it with that alias IPOS. And this will be inserted into my code wherever that constant is referred to. So again, since this is a compiler control feature, what the compiler is doing is basically cutting and pasting when it's going through compile time, when it's translating the code into assembly language. So for example, every time it encounters an inc rev in your code, it will replace that with a 4096. In every case it encounters an IPOS, it will copy that whole expression in its place. Again, you'll never see this. When you go back to your source file, you won't see everything replaced. It does this on the fly during compiling. Let me just remind you, it is really smart to comment every single constant and say what it is. And notice I've commented these pretty thoroughly. Again, that's for you if you've been away from the program for a long time. And it's certainly for other people down the road who are trying to figure out what on earth are these values. So comment, comment, comment. Now, variables. How are they different from constants? Well, I think the name says it all. Constant means it doesn't change. It's a fixed value of some kind. Variable means it can vary. It can change. A variable in the context of IPOS is just one of those slots in the MOVIDrive-B's data memory, and each slot can hold one 32-bit number. It's really just that simple. Remember, the slots are named H0 through H1023. We learned about this a number of sessions ago. Every single H value is one variable. So here's a case where we're referring to the variable by name. We're using its name, which is H1. That's the location in memory. We then have an equal sign. We call this an assignment. We're assigning a value to a location. And then finally, we have the expression. This could be as simple as just a plain old number, or in this case, it's actually the results of a calculation where we multiply two values and then divide by a third. So just remember, as the name suggests, the variable's contents can change during the program's execution, and it will, and that's what makes the program work. Another little reminder, not all variables may be used for general purpose storage. Remember, there are what are called system variables. They live between H453 and H560. The system reserves these for its own use, and while you can use them for certain things, you can't just use them for general purpose storage. You can't just dump your own information in there. If you do, you're either going to mess up your MOVI B when it's trying to run, or you'll just get bizarre behavior. So only use the system variables when you actually are using them in that capacity. The simplest way to use variables in your program is just use their H numbers, like this. H133 equals, and then you give it an expression of some kind. Throughout this code, you'll notice lots of H numbers in here. Okay, that is perfectly fine. That is a perfectly legal way of doing variables. Of course, you always have to be sure that you've picked valid H numbers that you're allowed to use. So you need to be sure to avoid using the reserved variables improperly. So always be careful about that. But a much better approach, and one that will prevent you from making unintentional mistakes, is to use a meaningful alias for each variable. I like this better. It's got the same rationale as using aliases for constants. It prevents you from having to always remember the H numbers and type them incorrectly, and it also lets you assign a meaningful name to each variable, which improves code readability. So you define them just right after the constants, and here are a bunch of variables. So how do we do this? Pretty much the same way we do with constants. We use the #define compiler control command. And then we give it a name. And you can use all lowercase or a mixture of upper and lower. Common convention many C programmers follow is to make variable names all lowercase, so you can kind of differentiate them from constants, which are all uppercase. And then, of course, right after the variable name, you have the H number it's connected to. Don't end the line with a semicolon. Compiler control commands are not ended with semicolons. But of course, you still have to choose the right H number. You need to be sure these are legal values and that you don't accidentally use the same H number for two different variables, which is usually a bad idea. So there are a few gotchas here, but this is an improved way to handle things. And it is a very, very smart idea to comment every single variable. So again, comment, comment, comment. Say what that variable is for. You will thank yourself, and other people will certainly thank you too for doing that. All right, time for another hands-on task. We're going to create a brand new file. Notice I say new file, program 2. I will show you how to change the source file in just a second, and then we're going to make some changes. So here's what we're going to do. Here's how you change to a new program source file. All right, presumably, you still have program 1 up, and we're going to use it as the basis for program 2. So we need to save it, so be sure you've saved it. And then we're going to do this. Do a save as, and change the name to program2.ipc. That'll create a brand new file in the same location. It'll leave the old one intact, so you'll still have it to refer to later. Then close the window holding the code, so just the editor window, not the whole compiler window. Right-click on program1.ipc on the left side. You can see I've outlined it in red. A pop-up menu will appear. Pick Remove from Project, so you're taking the old source file out. Then right-click on Source Module, and yes, that's a bit of German left in there. Sorry about that. And from the menu that appears, select Add Source File to Project. And then choose that new file that you created with the save as, program2.ipc. Double-click on it, and that will add it to your project, and you will now switch to a new source file. This is what you'll do all through the rest of the class whenever I tell you to change to a new file. So I'm not going to tell you how to do this again. So be sure you understand it. If necessary, jot it down, and we're good. All right, so what's going to happen is you're going to have program 2 open in the editor. It will look just like program 1, of course, because it's a copy of it. And now we're going to make some changes. And so here are what you're going to change. First of all, be sure to update the header comment since this is a new program. Change it to program number 2 and also maybe change the description. So always do that as a first step. Now, this existing program, which was the mystery program, remember, uses variables by directly referring to H numbers. We're going to now change this to do aliasing instead. So I want you to go through and find all the H variables and change them to these names: output, cycles, shift, and direction. So whenever you see an H0, change it to output. When you see an H1, change it to cycles, H2 to shift, and H3 to direction. And then, of course, you need to define those aliases for them. So back up in the variables and constants section, create 4 aliases using #define. Once you've done that, save it, compile the program, make sure it compiles fine, and make sure it still works. And if you've done that, then you've successfully switched over to using aliased variables. Once you get that working, here's the next thing to do. I want you to create 2 constants of your own called left and right and associate them with the values 0 and 1. Then go back in your program and look for cases where you see the hard-coded numbers 0 and 1 wherever the direction variable appears. Replace those hard-coded zeros and ones with left and right as appropriate. And then again, compile your program, make sure it works. Then come back in and do one last thing. Replace the hard-coded numbers in the wait statements with a constant called delay, and create that constant delay and set it to different values and see how you can affect the delaying in the program. So play with some different values. Every time you do a change, of course, you'll have to compile and try it out. So play with that, and that'll get your feet wet with variables and constants. All right, pause the video and go do it, and then we'll come back and I'll show you how I did it. All right, let's see how you did. I'm going to do it my way, and it should match the way you did it, hopefully. All right, well, we're going to make some modifications to program 1, and as the instructions told us, we need to switch to a new source file because we don't want to actually lose program 1. We want to keep a record of the programs we've developed and all the intermediate stages. So first thing I'm going to do is do a save as to make myself a copy of program 1. Program 1 is just fine. We're going to build on it, so I'm going to create a copy called program 2 by doing a save as. And what I'm going to do now is I'm going to close the source here, and I'm going to go over here to where it says source module, and if it's collapsed, I'll click the little plus symbol to expand it, but you can see it's expanded already. It's showing program 1 as part of the project. So I need to remove program 1 from the project by right-clicking on it, picking remove from the project and saying yes. Then I'll right-click on source module again, and I'll click add source file to project. I'll pick program 2, and then double-click on it to open it up. So this is what you have to do. You not only have to do a save as to create a new file, but you need to take the old one out of the project and put the new one in. Otherwise, when you compile the project, it actually will compile the old program, which could be very confusing. All right, so we've gotten everything in order right now. I need to do one thing. At the very beginning, I need to change my comment. So this is now program 2, and today is another day. It's actually January 31st. I'm going to change the description to and call this modified first IPOS program. So there, I've done my housekeeping. Now I'm ready to go ahead and do the assignment. Now, what are we doing? Very simple. We're taking all the hard-coded H variables out of here and we're replacing them with meaningful names. And so this is our first step toward making programs more readable using variables more intelligently. So I'm going to go down to the variables and constants section, which I've commented out here, so it gives me kind of a dedicated space for my variables and constants, and I'm going to create aliases for the H variables that are hard-coded in my program. And according to the instructions, I need to define output as H0, define cycles as H1, define shift as H2, and define direction as H3. So what I've done is I've created named aliases for those 4 variables, and those names are much more meaningful. So someone reading my program might actually have a notion what those variables do in the program just by looking at the names. All right, now I need to go and change the actual variables in the code. And of course, I could use search and replace for this, which is probably the smart thing, but I'm going to actually just do this by hand here, just so you can kind of see it happening. H3 is direction, so I just replace that. H0 is output, and I just go on through here and change them to match up with the new names. So H1 is cycles. And H2 is shift. H3 is direction. H0 is output. H3 is direction. H0 again is output. Yes, this is a bit tedious. That's why search and replace is so nice. H3 again is direction. H0 is output. And that is it. So I've now made all my changes. So I now have meaningful variable names in place of just meaningless H numbers. All right, let's make sure this works. I'm going to compile and load into the VFD. All right, no errors, so it's happy. And I'll click the lightning bolt to start the program, and then I'll go toggle DI10 just to make sure the chasing light works. And I'm not going to show that. I'll just confirm it works and come back and tell you if it did, because you've seen it work. Okay, I've confirmed my program is still good. It's still working. So I'm going to go ahead now and stop my program by clicking the stop sign, because we have some other changes we're going to do to the program to make it a little more meaningful. Specifically, add some constants. So we put constants traditionally ahead of the variables, and we were supposed to create 2 constants called left and right. So left is going to be defined as 0, and right is defined as 1. Notice constants are all uppercase. My variable names were all lowercase. That's a common convention in C. It just helps you tell the difference between what's a variable and what's a constant. What I need to do is find every place that the variable direction appears. And if it's got a 1 or a 0 associated with it, change it to left and right. So I'm going to go down through my code. And again, of course, search and replace could do this better. But here's a direction equals 1. So I'm going to change that to right. And I'm going to just keep looking through my code here. Here's another direction equals 1. So I'll change that to right. And here's a direction equals 0. I'll change this to left. And here's a direction equals 1. I'll change that to right. And that is it. All right, so again, by replacing those just 1s and 0s, which really didn't mean anything, with constants, with names left and right, I think we have a better idea what's going on here. Clearly, this is controlling the direction the ball's traveling. And that's what that variable does. That's what those constants are doing, is kind of setting the direction. So you see, this program is gradually becoming more readable. All right, let's run a compile. And we haven't made any mistakes, so we'll run the code. And again, I'm going to just go check it by flipping DI10 from off to on back to off just to confirm it works. And once I've done that, of course, then we'll go on and do our last change. So let me do that. Okay, and I've confirmed that the bouncing ball is still bouncing in the correct way. So that is good. I'm going to stop my program by clicking the stop sign. And I had to do one final thing according to the instructions. I needed to create a constant called delay. So we define delay, all uppercase because it's a constant. And we're going to replace those 250s in the wait functions with delay. So I'm going to define delay as 250. Just for your information, that's the number of milliseconds that wait function will wait. That's a quarter of a second. And the idea here is that by hard coding delays into the wait statements, if we want to make changes, we've got to hunt up all those waits and we've got to change them one after the other. If we create a constant instead, all we've got to do is change this one line, the define, to alter it. So that again makes changing your code a lot easier. So that's the argument for using named constants. So we need to find all the waits and replace the 250s with delay. So we'll put delay in here, and we'll look for any others, and here's two more, so we'll put these in. So there were actually 4 instances. If we wanted to change these, we would have had to do 4 changes every single time, and that's kind of clunky. All right, so I'm going to compile and run this, and just once again confirm that everything works. And I'm back and confirmed, yes, it works just the same way. All right, so the last thing we're going to do is we're going to see the magic of using a constant in place of hard-coded values. I'm going to stop my code, and I'm going to go up here and change my single delay constant value to 100 milliseconds to make it go faster. This will make it move at about 1/10 of a second. So just that single change is all it took to change all the waits down in the program. Let me compile this. And I am going to let you see this one run so you can see how much faster it goes. So here we go. We'll run our program, flip our switch. And as you can see, that was a whole lot faster. So I hope you kind of appreciate what we've done, how by using names and aliases and constants, we're making our program not only more readable, but easier to maintain and modify. And that, of course, is the big goal. All right, so that's it. We'll just stop our program here. We'll save it. And we are done. Okay, well, we're back now. Let's go ahead and continue learning about constants and variables. You know, it would be really nice if IPOS could automatically assign H numbers rather than making you look them up and use them yourself. So even though using the alias method is kind of nice, it would be nice if the compiler would do a little more for you. And guess what? It can. If you put the keyword long in front of a variable name, then IPOS will just automatically pick an unused H number and associate it for you. So this is really the best way of doing variables. So notice we have that keyword long, and then we have names after it. This first line has 4. This actually creates 4 different variables. Notice they're just separated by commas. The 2 lines below are just single variables, but each one of these will get automatically assigned an appropriate H number. So this is what I really like to do rather than using #define. But either solution is better than just using H numbers directly. I suggest all lowercase for variable names. That's a common convention, but some people like to use a mix of upper and lower. They're both okay. Your call. Just don't use all uppercase because that confuses people because they'll think they're constants. Do notice when you use the long keyword, you must use a semicolon at the end. And that is because long is actually part of the language proper. It's not a compiler command. I know I've said this a lot, but comment your variables. Explain what they are. Now, some miscellaneous information about variables and constants. Variable names and constant names must be letters, numbers, and underscores. No other characters are allowed, so you can't use anything but letters, numbers, and you can use underscores in place of spaces. 32 characters max is the longest a variable or a constant name can be. Now, you can do one handy little thing. If you put the word initial before long, that will tell IPOS to use the non-volatile variables, H0 through H127. And if you use just long by itself, it'll tell it to use the volatile H variables, H128 through 1023. So if you want something to go into flash memory, make it an initial long. Variables contain random values at startup, so you must set them to something definite. You can't assume they'll go to 0, for example. And there are many aliases already created in the two include files, constb.h and iob.h. And a lot of these aliases are really handy. You can use them for all sorts of things to make your program easier. Be aware there are no other numeric types implemented in IPOS. So if you're a C programmer or a derivative language, you may be wondering, well, what about integer, character, unsigned, floating point? Sorry, they're just not an IPOS. IPOS just has the long type, the 32-bit signed integer. Something else? All variables and constants are global. In other words, you can see them in every single part of the program. So they're not invisible. Other languages have what are called global and local variables, which are a bit different, but not an IPOS. All right, last thing we're going to cover in this session is some of the tools that are available in MOVITOOLS MotionStudio for debugging with variables. These are really handy tools. As a programmer, you'll come to really appreciate them because they'll make your life a lot easier when you're tracking down those difficult to solve problems. So what are these tools and how do they work? Well, you find the tool here under the display menu option in the compiler, and you pick the all variables option. What this is a monitoring tool that displays the complete data memory. You get to see all 1024 variables and the values inside, and you can see that right over there. Right now it's listing H0 through H44. They're all showing 0. Of course, you have to scroll down to see the others, but it is a complete list of every single variable. It updates in almost real time. Not quite, of course, because remember, it's trying to talk over that USB connection. It's not quite as fast as the program is running, but it gives you a pretty good idea of what's happening when the program runs. You can see those numbers change, and you can look at specific variables and watch them and see if they're doing what you expect. So it's a really nifty tool, and you're going to get some practice using it in just a few minutes. And here's another little nice feature of it. The reserved system variables are also identified automatically by name, so you can see their names as well as their H numbers, and that is really handy. You don't have to keep looking up the H numbers. You just look at the descriptive names. For example, notice status word is roughly in the middle there, H473. You can see that. That's a really great one to watch sometimes because it gives you a very clear picture of what the VFD is doing. So that's really nice. And if you've assigned names to variables in your program, either by setting them up with the long keyword or by assigning them an alias, then they will appear as well. And you can see your own names next to the variable as well as the H number. So that too is really helpful. You can also change the way the variable's contents is displayed. If you click on the row, you can pick the display format option and you can change it to display as a signed decimal number, an unsigned decimal number, hexadecimal, or binary. And you can also display an ASCII. That's the character equivalent that value would be if it were turned into a character. You mostly use that for communications and field bus kind of situations. If you're looking at individual bits, if you care about individual bits, then definitely go to binary because you can see those individual bits flipping. So if you're looking at something where the bits are significant rather than the number as a whole, that is really useful. Now there is an alternative to the all variables choice, and that is called the variable watch choice. You go to the same place, you pick the display menu option, then pick variable watch, and then pick open or edit window. And what you'll get is this. And what you do is you can go through a list of every single variable and selectively add them to the window on the right side using the Add button. And if you want to take one off the list, you can click the Remove button to pull it off. And what will happen is when you're using this, instead of seeing all 1024 variables updating in real time, you will just see the ones that you're interested in updating in real time. And they'll actually update faster because, of course, it's not having to watch as many. So right here, for example, I've got two variables in my watch list. I have H424, which I've called missed. That's a variable I created, and it's got a 0 in it at this moment. And then I've got that system variable, H473, status word. Notice I've got that set to display in binary, and it's showing the individual bits. So I can watch those bits flipping as the VFD is running, and I can see changes. Notice they break it up into groups of 4, which is really convenient. It kind of keeps the jumble of bits from being quite so visually confusing. So this is a great tool. I really like this, and you're going to use this a lot. And here's something else. You can directly edit variables as well. Notice, for example, H0 is being edited. If you double-click on the value, it will change to an input box, and you can type in a new number. And it'll change that variable right then and there. In fact, you can even do it when the program is running, which could get interesting and is often actually useful. So you can manipulate things as they're operating. So lots of good ways to play with variables. By the way, if you change H0 through H127, those non-volatile values, that actually will alter the flash memory. So those values will stick even when power is turned off. All right, time for a hands-on task. We're going to just continue using our existing program too, so you don't have to change files or anything. So here are the tasks. We're going to get acquainted with the variable debugging tools. I want you to run the program, and I would like you to watch H0, H1, H2, and H3 using the All Variables tool. So fire that up, watch every single variable change, but pay attention to those first 4 variables at the top of the list. Notice the speed at which they change as the program runs. And then once you've done that, stop the program, close the All Variables window, and set up a variable watch window containing just those 4 variables, H0 through H3. Run the program again and watch it update, and compare the speed. Notice how the speed changes when you just look at 4 versus all 1024. And then change the output variable H0 to display in binary format, and watch the bits changing in binary. I think you'll find that interesting. And as you're running the program, you can see what's happening. So some fun things to try. So go ahead, get acquainted with the debugging tool for variables. So pause the video, do it, and then come back when you're done, and I'll do it, and you can see how it looks for me. All right, well, let's see how you did. I'm going to do what hopefully you just did, and you can see how it worked. All right, well, our goal here is to explore some of the variable debugging tools that are present in the IPOS compiler. So what I'm going to do first is just make sure that my program is freshly compiled and loaded into the VFD. This is the program we had earlier, so it probably is still there, but I'm going to do this anyway because if you don't do it, sometimes the variable watch won't show the names that you've assigned to variables, and we always want that if possible. Okay, so that's all set. I'm going to go over to Display and pick the All Variables window first. This is the one that displays every single variable, all 1024 of them. And you can see right here the ones that I've created, output, cycle, shift, and direction, are there by name. We can see their values, and of course if we roll down here, we've got a lot of others that are empty at the moment that aren't in use, but when we get to the system variables, you see that they're colored in red, and they all have names. So lots of things here that you can look at, but we're not interested in those right now, so we'll go back up to the top. What we're going to do is run the program, and we'll see how the All Variables window handles things. So I'm going to click the lightning bolt to start the program. And of course, I have to toggle DI10 on and then off to start the program running. So go ahead and watch the 4 variables, output, cycle, shift, and direction, and kind of get a feel how they're changing as the program runs. All right, as you can see, they did change as the program ran, but they really didn't seem to be particularly in synchronization with what was happening on the lights. Of course, you can't see the lights, but I can. And the reason is when you're running the all variables, it's got to update all 1024 variables constantly, and it can't quite do that as fast as the program is running. So what we're seeing are actually snapshots of what's going on at different times. We're not seeing really the complete picture. All right, so a better way is to use just the variables that we're interested in. So I've just stopped the program and I'm going to close the all variables window. Okay, I'm going to go to display and I'm going to pick variable watch and pick edit window. This will allow me to pick just the variables that I'm interested in. So I'm going to pick output, and I'm holding the shift key down to select multiple ones, cycles, shift, and direction. I'm going to click add to put them in the watch window. These are the ones that we're actually going to see. It's going to ignore all the others, so I'm going to OK that. And that opens a watch window here. And you can see just those 4 variables are now being updated. This should go a little faster. I'll click the lightning bolt again. And then I'm going to go flip the switch, and you can see these, and I think you'll notice they're updating more realistically. All right, so that really kind of illustrates the value of just watching what you care about. It's still not real time precisely, but it's a lot closer. Now let's make a change here. I'm going to stop the program. And I'm going to change my delay constant to a little slower here. We'll go back to 250 milliseconds. Of course, we have to recompile and reload our program. And now I'm going to get my variable watch window back. And I'm going to change the output to binary. Right now it's displaying in decimal by default, but if I right-click on output, pick display format, and pick binary, you notice we now see the individual bits making it up. I'm going to run this, and I'd like you to watch the lower bits, the ones near the least significant bit end, as I run the program. Remember, we have the bouncing lights, and I've slowed the lights down a little bit, so I think you'll be able to see a relationship between output and what the lights would be doing. So I'm going to click the lightning bolt, start it up, and go ahead and click the switch to start it running. I think you can notice that the bits are sort of moving around like the lights are on the display. In fact, this output variable is what's controlling the lights, so it's being shifted back and forth. So there is definitely value in going into binary display sometimes if you're really interested in what bits are doing individually. All right, so that illustrates using the variable debugging tools. Those can be a real lifesaver if something in your program just absolutely mystifies you and you can't figure out what's going on. You can look at the variables as the program runs and get an idea maybe what's wrong. So we're done. And that is the end of session 4. Hope you found that helpful and interesting and feel that you now have a good grasp of variables and constants because you will certainly be using them a lot in the sessions ahead. So see you next time.